for this insightful session. Today, we are privileged to have two distinguished speakers from Niral Networks Pvt Limited, who will be sharing their expertise on key aspects of 5G technology. 5G RAN, 5G core networks, and 5G MEC by Mr. Sivaramakrishnan, control and data path architecture and IMS by Mr. Venkatesh. We encourage you to actively engage, ask questions, and make the most of this learning opportunity. Now, let us proceed with our first speaker, Mr. Sivaramakrishnan, as we continue from the previous session. Over to you, Mr. Ramakrishnan.
Good afternoon, everybody. So we'll continue our presentation on the 5G architecture. So basically, what you see on the diagram are the different subsystems. One is the G node B, and another is the UE. And the third important component is the core network. And optionally, we can edge cloud as part of the system. So we will go a little deeper into all these subsystems and then see some subtle architectural aspect as well as subtle design aspect that will help us understand the overall system in a greater detail. So let us take the interaction between an UE and a G node B. So basically, before a UE connects to the radio G node B, it has to do basically there needs to be a cell selection procedure and a synchronization procedure. So this synchronization procedure needs to be done on both the uplink and on the downlink. Say, for example, when we talk about the downlink synchronization, that is, we have a mobile, assume that it is a 5G or 4G mobile. It has to first get recognized by the network. And then based on the basic synchronization that is established, further control path initiation from the UE to the base station and to the core happens. So when always the base station is trying to do a downlink synchronization, and then basically it invites different
recording in progress.
Basically invites various registered UEs to get connected to the radio G node B or RAN whenever the UEs are powered up. So as part of the downlink synchronization, the RAN or G node B keeps transmitting certain information such as MIP and SIB 1 to 2, 3, 4, etc. So if we see the crux of this information, they are specifically something like which outlines the frequency, bandwidth, PLMN ID of the network. They are all getting broadcasted continuously. So it is the responsibility of the UEs to read these downlink synchronized information that are available in the MIB and the SIB, and then appropriately initiate an uplink synchronization, which is called RATCH. And as part of the RATCH, what an UE attempts to do is that it basically tries to get hold of a slot, and the RATCH is negotiated with a preamble. That is, UE trying to get hold of a preamble to initiate further communication to the RAN or G-Node B on a continuous basis. So by preamble, it is you can assume that there are different slots on which the UE can uh, communicate on the uplink. And then these slots are pretty much allocated for the UEs. So it is the responsibility of the UE to initiate a RACH procedure and negotiate a particular preamble. You can assume that that is a slot. So that on all subsequent communication, this particular slot can be used. So this is the main procedure in a very brief as to what happens, how a mobile phone, for example, gets the basic synchronization, establishes the basic synchronization between the mobile and the RAN, which is very important. After this, when this uplink synchronization is successful, is when an UE can initiate whatever call it as a UE attach from the UE to the RAN. So this is one important procedure of entire I would say the basic communication between the UE and the radio unit. So let's move forward here. So we saw different component yesterday with respect to the 5G core and how the different control path and data path are handled. So what you see in this diagram is a little more breakdown of at a protocol level and at an interface level. Basically also with respect to the bearer establishment across the G-Node B and the core and the UE. So let us start with the diagram at the bottom. So let's start at the interface level. So this is one generic diagram, but the important point what you will have to look at here is the N2 and the N3 interfaces. So we discussed about there is a control path between the G-Node B and the core in the 5G. And the communication on that level happens through the N2 interface. That is, you might remember the communication between AMF at the core and to the RAN. So that is one important interface. And another interface is the GTP tunnel that is established between the RAN and the core. These are to forward data packets over the bearer that are established both in the core and the RAN. So so these are the two important interfaces through which the communication happens, both in control path and data path. And if you see on the diagram on the top, basically it illustrates different protocols that are used to get these work done. If we look at the stack at the extreme left, which tells NGAP, SCTP, IP, so this caters to the N2 level protocol where the basically all the flow initiation happens through this protocol. So basically, if we take a control packet, so that might have an NGAP header, and then it has a PDU within that. And then that is encapsulated into HTTP for a more secured communication, and that within that is the IP packet, right? So this is how the communication happens on the end-to-end interfaces to negotiate various control path communication. Once the bearer is established, between the core 5G core and the RAN, we have a tunnel established, and then the tunnel goes through the protocol GDP. And of course, a GDP packet is again encapsulated by UDP. Then over that is the IP. Basically, all communication between the G node B and the core are identified on a tunnel between these two endpoints. So if you can see the diagram on the top right, it clearly indicates the bearer paths that are established between the 5G core and the G node B. And this is illustrated for one particular tunnel, that is one particular UE. So you can see that now in a tunnel, basically there are different QoS flows. We'll come to that. But if you see the interface between the G node B and UE, these are radio bearer paths. So what you can see is that for a particular UE, depending upon the service flows, there can be multiple radio bearer paths that are established to take care of the communication. And then when they are transported over the N3 interfaces, they go through one particular GTP tunnel. So this is how the flow is established. And when we talk about the GDP tunnel and the radio bearer, they are all getting created through the flows when the PDU sessions are established. We saw yesterday that after the authentication procedure, there is a PDU session establishment that happens both at the core and at the radio. So these radio bearers that we see between UE and G node Bs are created as part of that handshake, and this facilitates an end-to-end bearer path flow between UE to G node B to the core. So this is overall how the bearer paths are established. And here, one more important aspect of 5G is at every subscriber level, we can implement different QoS that can be implemented. A particular subscriber can have one or more QoS flows that it can be subscribed for. And there are priorities within these QoS, and then based upon the priorities, the scheduling also happens. Say, for example, if we have different services, let's correlate this from an end-to-end service. Suppose you have a plan with the operator, and as part of that, you can do a voice call and internet access. Two scenarios we'll take. So for both these scenarios, what we have is that as part of the SIM subscription, we will have different QoS that are assigned. So this particular subscriber will have a QoS for an internet access and another QoS for um, another QoS for the voice access. So when PDU sessions are created, there is one PDU session that are created for internet and another PDU session created for voice. So, and as part of the subscription, we can also define the priority in terms of QoS values. It is called in 5G as 5QI. So a voice will have a 5QI value of 1 and an internet access will have a 5QI value of 9. That means that when there is a voice communication and the internet access, voice communication will be given more priority. That is, QoS PDU sessions with lesser 5QA value will have a higher priority. So like this, 5G supports up to 64 5QA values for different implementations. Say you subscribe to a emergency service. In some places, PPDR services are implemented. So they will have more 5QA priority than compared to an internet. So this is how within a barrier we can have multiple PDU session, or you can even correlate a PDU session to a barrier, and then basically across these PDU sessions, basically the system handles these QoS PDUs at a different priority level. So lower 5QA values are scheduled before higher 5QA values. And what you see on the top left-hand side, there is an SDP protocol, SDAP protocol. This is a service adaptation layer. Basically, all the QoS creation and the scheduling across them are handled at this layer. So basically, any traffic coming from the UE, they go through a MAC layer where basically we have packets to a prescribed limit that are set so that the communication with the lower L1 layer is facilitated. Then these MAC layer packets are given to RLC, which takes care of the conversion between the lower MAC and the upper PDCP layer. The PDCP layer basically handles all the security check, etc. Then above layer is the SDAP layer, what we saw a little earlier on the QoS PDU scheduling. So overall, this is the implementation. On the UE facing side, we have these protocol stack, which cater to both control and data path. And when it comes to the 5G core facing side, we have two interfaces, N2 and N3. N2 taking care of the control path, and those are handled by the protocol stack NGAP SCTP. When it comes to the user plane, it is handled by the tunnels, and those are the GTP packets. So this is how at the RAN in terms of both control and data, and basically how the different PDU sessions are handled, handling the priorities across them. So any questions so far? Okay, we'll proceed. So I will. I have a couple of slides. Venkatesh will be taking in detail the control flow, whereby he will be also handling the functionalities at the 5G core network functions. But a little overview on them is we saw yesterday that among all the network functions, there are about 3 of the network functions which are very important. The AMF, this handles the control path. So as part of that, it handles the registration, authentication. Then it also interfaces with other network functions such as AUSF, UDM, UDR for authentication and key agreement, security, and user identity related detail. And with respect to interface, it handles N1 interface for the NAS and the N2 interface for the NGAP. The second important network function is the session management. So basically, it handles all the, I would say, the PDU session creation within the 5G core, interfacing to the user plane function UPF. And it also interfaces with PCF policy control to derive the different characteristic for the PDU, such as the QoS. We just saw the different 5QI values. And then there are other features such as rate limiting. Say, for example, on a particular PDU, we want to rate limit and assign that this particular subscriber cannot go beyond 100 Mbps on the uplink or 100 Mbps on the downlink. Then those type of rules can be specified as part of SMS. Then we also have the functionality of IP address assignment um, that is primarily driven by SMF. Say, for example, a UE connects. It does a proper control path communication, and after that, it needs to be assigned an IP so that it can properly communicate over the user plane. So the responsibility of assigning an IP to a set of subscribers is basically driven from the SMS. So here again, you can group a set of UEs and then assign them a particular domain IP address, a particular subnet, and then this can also help us assign this set of UEs to a particular DNN, and then we can associate that particular subnet to the DNN. So at a UPF level, what we can do is we can basically make it more flexible and then route a different set of subnet users to different interfaces. So one more point I would like to highlight here is 5G recommendation as such mandates some flexibility in terms of, basically the backbone is an virtual architecture, right? Which means that dynamically you can spawn, or even statically, depending upon your traffic design, you can spawn multiple UPF or multiple AMF to segregate your data flow. Meaning you're designing a private network and there are about 100 subscribed user as part of that system. Assume that you want to categorize as 3 different groups, and then the 3 different groups can be associated with one particular subnet each. And then you want to handle traffic separately. Then what we can do is that in the system, we can create 3 UPF. And then basically what we can do is that to each of the group, we can assign a separate UPF so that the traffic is handled very efficiently. Mm. That is one big advantage in 5G. So if you want to think little futuristically, you can 5G gives a flexibility of keeping the control path in the cloud, and you can um, uh, keep the user path quite local to the user, meaning like you have a small network where you have installed a RAN, you can have a edge cloud there, and you can run an UPF there. The advantage being that any call, and you can connect a lease line in that premise, and then only the control path is negotiated on the cloud, but the data path from the RAN is directly routed to the UPF that is local in the system. So these are all the real flexibility that 5G is bringing, leveraging the virtualization um, backbone or infrastructure that and the entire network can make this happen quite dynamically as well, based on the implementation. Similar to AWS spawning multiple VMs over a weekend to handle online retail traffic, we can also design the system in a flexible way. Say, for example, in the morning hours, there are more traffic, so you can spawn multiple UPF and handle the traffic better. So those are the real breakthrough changes that can be feasible using a 5G um, infrastructure. So just wanted to highlight on these points, and couple of other important points with respect to at the high level view on the 5G core network function are there is a network function called SCP, Service Communication Proxy. So basically, it helps um, all network function to communicate uh, through that. Say, for example, we have an SBI interface where it is based on HTTP, and then we saw that there are N2 N3 interfaces that communicates to RAN and outside DN, but the communication between an AMF and AUSF is through the SBI interface. And then these communication, say basically these might be some service calls. That is, AMF will get a registration request from one UE. It will call AUSF, and it will tell, please confirm whether this particular EMC number is configured in our database. So AMF communicates to SCP, then SCP communicates to the AUSF, and on the backward direction also, either a response or a JSON data from AUSF is transferred to AMF through an SCP. So this layer basically controls a proper flow mechanism between different network functions. Another important network function is NRF, Network Repository Function. So basically, this provides a sort of an heartbeat mechanism. That is, every network function sort of updates that it is in a good health periodically to NRF. And then this basically helps to keep a track of the basic availability of all network function. So we were talking about the NRF. So NRF basically has a first-hand information about the dynamic availability of all network function. So these are some of the important a key aspect of the communication. And NRF also one other aspect in a virtual containerized implementation, where we'll see in the next slide that each of the network function is implemented as a container. And basically this registration and health check with NRF also helps to restart the services if there are any particular um error scenario due to which a reset of one particular network function is mandatory. So basically we saw the RAN in some detail and the control path, the data path, and certain important concepts around that. Now here we will have a quick look at basically the virtualization infrastructures, the key component, how the different VMs in the whole 5G core edge cloud architectures are implemented. So basically, as part of 5G core, we have all the network functions that run as part of one container, which is basically as per implementation, it can implement all the network function as containers, part of the core. And basically here the key challenges are to export. Basically it works on a Docker framework. So your physical Ethernet IP is bridged to your VM's IP, and then that internally a sort of is connected to the Docker bridge, and basically from the VM we can ping any of those network function in terms that it's how the SBI interface communication happens within all the network functions. But here another key thing is the exposure of N2 and N3 API, because these are the interfaces that need to be visible for even a RAN to communicate. So we saw that through N2 the control path, and through the N3 the data path communication happen. So typically the implementation is that the exposure of these interfaces are done through MAC VLAN. And similarly, if in an IMS architecture, also each of those control functions are implemented as a container in an IMS VM, and the communication between the core and IMS VM is possible through a VM interface communication. And another important aspect here is a controller functionality, basically providing a management portal where you can, through that management portal, you can configure the subscribers, and then you can configure other parameters in the core, and similarly in the IMS as well, so that a proper control path communication, say creation of a network slice, all those details can be carried out through this management portal. So these are the typical standard design approach through which on a type 1 hypervisor we have multiple VMs. Those are created, and as part of deployment they are deployed as Docker containers. That is one implementation how we can do. And So these are basically controlled by the controller management portal. So that is how a core software at an instance level or a VM level is getting implemented. And similarly, another aspect what I would like to highlight is that the way it is implemented is the way the edge cloud is implemented. Normally, through the management portal, through those interfaces, provisions are given to access an hypervisor and then to create multiple VMs. And in each of the VM, we can run applications which are basically used for various local communication as part of the edge cloud. Say, as given in this slide, if you want to create a particular VM in which you want to have a video streaming server and also video analytic application. So basically, you create a VM. Then as part of creation of VM, you specify the characteristic of it, like the memory, storage, number of cores. And then you can also basically create or associate a particular operating system which can be booted onto that particular VM. And then we can define a set of interfaces so that the various applications can use as part of communication once the VM is up. So this way, we can create a VM and then we can install the required application as part of that framework. And then we can also have some management portal access to monitor how much CPU used, how much memory is used. And once these applications are made available as part of these framework, then any UEs or CPEs that are getting connected to the private 5G infrastructure can have an access to the applications that are locally available as part of this VM. So this is how the virtualization in infrastructure is implemented, both for the 5G core as well as the edge cloud architecture. So this completes the first part of our session today.
So I would like to request Mr. Venkatesh ji again to start the session and let people enjoy. Thank you.
Yeah, thank you, Sanjay ji, for your warm welcome. Is I audible now?
Yes, you are very much audible.
Okay, let me start. Let me first introduce myself. I'm Venkatesh, working with a senior software engineer in the 5G core team at Niral Network. Some of the key projects I worked on include like entry-level view and statistics module. Like in today's session, I will be covering some of the topics like 5G core architecture and functionalities of each 5G core network function, a registration, PD session, establishment call flows. And finally, we'll walk through the Wireshark pickups capturing a live environment. So before we start the architecture, let me give some introduction about the SBA architecture. In 5G, all control plane network functions communicate with each other using a service-based interface. Like SBA stands for a service-based architecture and it follows a consumer's producer model. SBA architecture is one of the key reasons why 5G core is highly scalable and flexible. After initialization of all network function, like all the control plane network function, first it registered with NRF using the SBA interface. Like during the registration time, NRF stores some of the key parameters like network function capabilities, IP address, and services provided by each network functions. In SBI architecture, a consumer producer model is used. A producer is a network function that provides services, while a consumer is a network function that requests or consumes a service.
Hello, sir. Sir, we are not able to see your screen. We are seeing Sivaramakrishnan screen, sir.
So, like,
I think with same login he is presenting, but
Okay.
whether PPT you can see or not.
Yes, sir. We can see.
Okay. So I think first PPT is going on. Okay, 5G architecture and block diagram. All are requested to mute themselves so that it will go properly. Okay. Thank you. Thank you very much.
okay, let me continue. In SBI architecture, a consumer producer model is used. Like, a producer is a network function that provides the services, while a consumer is a network that function that requests or consumes a service. For example, during the authentication procedure, AMF acts as a consumer by requesting the authentication parameter from the AUSF. Like which here the AUSF acts as a producer and AMF acts as a consumer. And now let's discuss about the CUBS architecture before we move to this. CUBS stands for control plane and user plane separation. Like in 5G, we use a concept called CUBS, which means separating the control plane and user plane separation. This helps make the network more efficient and flexible. In control plane, which manages network functions like authentication, session control, can be placed in a central cloud. Meanwhile, the user plane function, which handles actual user data, is placed closer to the radio access network. Since UPF carries the real data traffic, keeping it near the RAN, it reduces the delays and improves the speed and functionality as well. One big benefit of this separation is scalability. With a centralized control plane, one system can manage multiple VPFs depending on the network operator's needs and user traffic. This makes it easier to expand the network without affecting performance. Another key advantage is it will give you the lower latency as well. Because user data doesn't have to travel long distance, placing near the UPF near the RAN, it speeds up the data transfer. This is especially important for applications that needs a real-time response like online gaming and set-driven cards. Okay, let me give some overview of the AMF. AMF stands for Access and Mobility Management Function. It is one of the key control plane functions in the 5G code. It's responsible for handling the UE registration, mobility, authentication, security, and session management support. It acts as a first point of contact for the user equipment when it comes to the network. Some of the key responsibilities of the AMF is when a UE powers on, it must first register with 5G network. AMF handles this by processing the registration request sent from the UE via the G node B. It assigns a temporary identifier called 5G GUT. GUT stands for Globally Unique Temporary Identifier, which helps in future communication without revealing the real subscriber identity. Like INSI and SUKI, it no need to be revealed over the ad interface. If the UE goes into the inactive state, like in RRC inactive, the AMF maintains the context and receives the connection when it needed. And one of the next functionality of the AMF is mobility management. Like AMF is responsible for tracking the location of UEs within the network. It maintains UE location information using the tracking areas and updates the UE location when it moves to the different areas. When the UE moves from one GNODP to another, the AMF facilitates the handover process as well. Apart from that, it will helpful for the authentication security procedure. Like AMF will interacts with AUSF over the SBI interface to verify the UE's identity. It also retrieves the subscriber information from the UDM and UDR as well. Like the subscriber information such as like the SUPI or key and OPC. And during the session establishment time, AMF has to identify the appropriate SMFs. Like when a UED requests the data connectivity, the AMF is responsible for setting the most suitable SMF. The selection is based on various factors such as network policies, subscription profile, and the location of the UED. Next, we move to that session management function. that's shortly known as SMF. SMF handles the PDU session management, like EE IP address allocation, policy enforcement. It takes to data plane over the N4 interface using the PFCP protocol. Some of the key responsibilities of the SMF is PDU session management. Like a PDU session is required for EE to access the data network. SMF is responsible for creating, modifying, and releasing a PDU session within a UE request connectivity. It supports multiple PDU sessions like IPv4, IPv6, and even the Ethernet for some industrial application as well. SMF allocates an IP address to the EU during the PDU session establishment procedure. It assigns either IP address dynamically or fetches them from an external DSCP server as well. Then, it will select that appropriate EPF also for that GTP tunnel. Like it sends some rules and traffic routing policies to the EPF via the N4 interface. The only network function which talk to the data plane is SMF. And other responsibility of SMF is it will useful for the QoS quality of service and policy enforcement. SMF configure QoS rules based on policies received from that PCF. It ensures different application like voice, video, and gaming, and get the required priority and bandwidth. Next, we move to that user plane function. UPF, it stands for user plane function. It is responsible for handling the user data traffic. After a successful PDU session establishment between the UE and the UPF over the G node B, all user traffic flows through the data plane encapsulated with a GTP header. UPF processes the packets by removing the GTP header and forwards them to the data network over the N6 interface. When the response is received from the data network to the UPF, it adds the GTP header back and forwards the packet to the UE using its IP address and tunnel ID endpoint identifier. Some of the key responsibilities of the UPF is, like in 5G, not all network traffic is treated the same. Some services like voice calls or emergency communication needs higher priority and guaranteed performance. This is where QoS comes in. Like UPF is responsible for making sure that different types of traffic get the right priority and speed. It does this using the QoS policies provided by the SMF. Like some of the 5QA parameters, like 5QA9, it's used for the normal internet data, and 5QA5 for the VoNet SIP signaling, and 5QA1 for the VoNet audio calls. And some of the examples, like if you take like mission critical applications, 5QA69 is used for that M6 signaling, and 5QA17 used for that M6 data, like sending messages or images. 5QA65 used for the M6 audio, and 5QA67 it's used for the M6 video. Like some of the interfaces used shared by the UPF is the N3 interface. It transports the user plane data between the G node B and the UPF. It uses the GTPU for encrypting the data packets and ensures the secure optimized data forwarding from the EU to the core network. And another interface it's shared with the data network between the UPF and the data network is the N6 interface. It is used to if you want to communicate with any of the public internet or any of the enterprise network, this interface will be useful for to get that user data from the data network. And like N4 interface, it is there. Like I previously explained about that as well. Next, I'm going to talk about that PCF. Like PCF stands for Policy Control Function. It manages and enforces the network policies. It acts as the brain of policy management. It ensuring the data, different services receives the proper quality of service, charging rules and access control policies. Unlike traditional 4G network where policies were outcoded in the different network element, 5G introduces a centralized PCF. It's allowing a dynamic and flexible policy enforcement. And PCF will helpful for the charging as well, charging and billing. It will talk to that CHF network function. It will helpful for the charging and billing as well. The charging, it may be based on the data volume and service type and time of the day when they are using, how much data they consumed by user. And next I move to that UDM. UDM stands for Unified Data Management. It is responsible for managing subscriber data, authentication and network policies. It serves as the centralized database that stores the essential information about the users and their access permissions. Like in 4G network, we known as HSS, that is called it as home subscriber server. But in UDM, in 5G, it's a cloud native. It's more flexible and supports dynamic policy enforcement. Next, I move to that AUSF. AUSF stands for the Authentication Server Function. It is a crucial security function in 5G core network. It is responsible for authenticating the user and devices. Like if any of the UE want to be get the service from the core network, it first need to be authenticated by the core network. So for that, the AUSF will be helpful. It ensures only the allowed subscribers can access the network by verifying their credentials. Like some of the key responsibilities of the ASF is ASF authenticates the user based on the credentials stored in that UDM. It works with the UDM with the N8 interface and ensures a secure authentication for both SIM-based and non-SIM-based devices. Like it supports for multiple authentication methods like a 3GPP AK authentication key agreement and extensible authentication protocol. 3GPP AK is used for that SIM-based authentication, like it's for the 3GPP authentication. If any of that you want to be connected over the non-3GPP, like over the N3 for the Wi-Fi access point, on that time it will use that EAP protocol to authenticate. Okay. Next, I will move to the NSSF. NSSF stands for Network Slice Selection Function. It is responsible for selecting the appropriate network slice for user equipment. Like network slicing is one of the most important features in 5G. It allowing operator to create multiple logical network within a single physical infrastructure for each different use cases, such as EMBB and ultra variable low latency. This may be more useful. NSSF interacts with AMF and PCFR slice enforcement. And at last, I'm going to talk about that NRF. NRF stands for that Network Repository Function. It enables the service-based architecture by providing the dynamic discovery and registration of network functions. Like unlike previous 4G network, where network elements and had predefined static connection. But in 5G, introduce a more flexible and scalable architecture where network functions can register and dynamically discover each other using the NRF. Like first, UE sends a registration request to the AMR via the G-Node B. This message contains that like a UE identity, maybe a SUPI, SUKI or duty, and registration type. The registration type in the sense like it may be the service request or emergency request or like initial registration request. This message indicates it wants to attach to that core network. Then AMF sends an identity request to the UE through the G-Node B. It's asking for the additional identity information. In the first registration request, if the UE sends the GUI, but if the GUI is not allocated by this AMF, on that time, like AMF not able to recognize that UE is served by this network or something else. So, like GUI is the temporary identifier. It will be allocated by that AMF. But if not able to identify, it will again ask for that identity request. And again, in the uplink message, we will send the identity response. The identity response, it will send that SUPI and SUKI. After AMF receiving that identity response, it will talk to that AUSF for that authentication using the UE authentication service. Then AUSF will talk to the UDM to fetch the security related information, like including the authentication vectors. Then UDM retrieves the UE subscription data from UDR, including the authentication related parameters like a key, OPC, and IMC. And UDR in UDM confirms that the requested subscription data is successfully retrieved and sent back to the AU server. After that, once AMF receive that authentication vector from that AU server, it will send the downlink authentication request to that UE. After that, UE calculates that authentication response and sends back to the AMF. And again, AMF sends this authentication response to that ASF for the verification. Then after it's verified, UDM is notified about the authentication event for that UE, and UDM queries the user to confirm the updated subscription data after the authentication. Then UDM confirms the data update and status is propagated back to the AMF. After once the authentication procedure is successful, AMF will send the downlink NAS transport message. In this message, it will include the security mode command. This message is useful for the ciphering and integrity protection of the NAS signaling. Like,
sir, excuse me, sir. Yes, sir. What is the 200 OK, 200 OK? What is that number actually indicating?
Okay, actually, this is the HTTP based message. Like whenever any request sending by the AMF to that other network function, like if any of the consumer want to get some services from that other network function, on the time first it will send the HTTP request. So based on that, if it was successful or failure, if it is successful means it will send the producer network function will reply with the 200 OK.
Oh,
yes. Along with it will send some parameters like authentication vector parameters like SQM parameter and the authentication token. It will share back to the AMF to complete the authentication procedure.
okay, sir. Thank you, sir.
Once AMF asks for that security mode command, like AMF will tell what are the integrity and ciphering encryption it will support by the core network, and later UE will decide, and again it will send that security mode complete message. After that, AMF receiving the security mode complete message, it will talk to that UDM, inform the UDM about the registration for the 3GPP ASIC storing the context data. UDM stores the registration context data in the UDR. And again, if the UDR after successfully storing that context data, it will UDR will respond with the 201 created. The same like UDM will respond back to that AMF with the 201 created. After that, AMF request subscription data related to the UDs, ASICs and mobility from that UDM for this AM data service. So that UDR queries this UDR to retrieve the requested AM subscription data, and UDR confirms the retrieval of the AM subscription data which is sent to the AMF. Then AMF requests SMF to select the data from the UDM to prepare the PD session establishment. Then UDM queries the UDR for the SMF selection related subscription data, and UDR confirms the retrieval of the SMF selection data, and it is sent to the AML back again. Then AMF contacts the PCF to establish the policies for the UE over that NPCF AM policy control service. Then PCF queries the UDR to retrieve the policy data and related to the UE. Then UDR confirms the policy data retrieval, and PCF sends it to the AML back. So at last, when the policy related things are created, PCF will reply back to the AMF with the 201 created. Then AMF sends the registration accept message to the GNODB to set up the initial context setup for the UE. After this, like UE radio capability information will be exchanged. UE shares its radio capability information with GNODB, which forwards it to that AMF. Then insert contest setup response GNLP confirms the successful establishment of the insert contest setup for the UE. At last, the registration complete will be happen. Then UE notifies that the AMF that the registration procedure has been completed. After that, if you want to access that services, it want to send that PD system establishment request. After further that, the configuration update command will be sent by the AMF to that UE. In this, AMF will send that a network name and a particular current time zone or that. Then AMF requests the SMF to establish the session management context for the PD session. Then SMF queries the subscription data from the UDM and gets the response. And the UDM retrieves the subscription data from the UDM for the requested session, and it replied with the 200 OP created. When the SMF gets that information from the PCF, people send the PFCP session establishment request to that EPF over the N4 interface. And during this time, PFCP session establishment request, SMF will tell the UE IP address and the tunnel ID and what are the policies it want to be useful for this. In this time, it will share the QoS profiles as well for this particular session. And once the session was established, EPF responds with PFCP session establishment response. Then SMF, the same thing, it will convey to the UE over the AMF. The P3 session was at last accepted. And then between the AMF and GNLP, the PD resource setup will be happen. During the PD resource setup request, the AMF will transfer the what is the tunnel ID assigned by the SMF to that EPF and what is the IP address allocated for that. These are the things it will be shared by the SMF to that. So this is the brief call flow during the registration time and in the PD session establishment time.
Sir, I have doubt in the network architecture diagram.
Okay.
So what is that BSF function, and also in SBI interface for every network function it was showing some NNSF, something like that. What are the terms say?
Can you repeat your question once again? I didn't get your question.
Sir, BSF function. I didn't get about the details. BSF.
Okay, actually,
And
the binding security function, it will be useful for it want to be make any session related information. SMF will talk to the BSF and will get that some of the additional session related information from the BSF.
And also in the SBI interface for every networking function, there is like a NNSF, NNRF. What are the terms used?
Usually, that it's called as each interface name. If any of the network function, between the AMF and SMF, that interface name dedicatedly called it as a N8. The same if that is kind of a service provided by the AMF, like a NAMF services, like it may be that authentication service, or if a NASF means ASF will provide the authentication service. Like what are the services provided by that ASF? Everything will be talked over the SB interface. So here they mentioned as a NAMF, NSMF, like to indicate that services.
Yeah, Mr. Venkatesh, I have put my question in the chat box. So we are talking about the latency. So how much improvement we can see in compared to previous generations like 4G or 3G? So in terms of services, if I will talk in terms of railway and metros where the high-speed trains are running at 250 kilometers per hour. And if I'm using the video services like sending the CCTV stream from train to control center or browsing the internet. So how much latency we can expect there?
Like usually 5G will offer the 10 milliseconds, less than 10 milliseconds. But if you keep the data plane near to that your radios, even though that your MEC application and VPF, it's very much near to your RAN, it will reduce the latency compared to the previous 4G network.
Okay.
It's based on that how deployment also. Like if we keeping that data plane and our MEC kind of application very much near to the RAN, on that time it will possibility of reducing the latency also very high. Okay, now let's go through the some practical outflows of a 5E registration and P registration establishment provision. This log we captured during that action. In this log, we only covering that message flow between the GNode B and EMF. Like you can see the packet number 6977. This is the UE registration initiation. Like the UE initiates the registration process by sending the initial UE message to GNode B, which forwards it to that EMF. This message contains the, let me work on this packet. So it usually inside the encrypt message, it will encapsulate the NAS message. So NAS is the N1 protocol. It's between the UE and the core network. In the NAS message, it will share that some of the main parameters during the registration request is like 5G's mobile identity. Like here, it's sharing the SUKI, but in the 4G, it will share the MC. In 5G, it will share the SUKI. The SUKI is the combination of MCC, MNC, and the MC number, which is totally a 15-digit number. And apart from that, it will share the UE security capability also, like what kind of encryption and integrity algorithm it will support. So this is the first message. It will come from that UE to that EMF core network. After that, in packet number 7162 and 7168, the EMF challenges the UE with the authentication request. Like after the UE known, this SUKI already, it will the EMF will query to that UDM and get that is already is the UE is already the valid subscriber. After that, it's further proceed to that authentication request. Like in the authentication request from the EMF to the UE, it will send some of the key parameters to calculate that authentication by the UE. Such a parameter is called AU10. This is the authentication token and followed by the sequence number and authentication management field and MAC address. So based on these parameters, again UE will find that 5G algorithm and it will send the response back in the authentication response message. So in the authentication response message, it will share this 32 bits number. So this is the authentication response parameter from the EE to that AMF. At last, if that so already the AUSF will read that on authentication expected authentication response to that AMF. So AMF will compare both the response from the AUSF and the UE. If both are matched, then it will allow to proceed further. Otherwise, during the authentication process itself, it will be get failed. You will not allow to register. And next is the security mode command. After completing the authentication procedure, it will move to the security mode command. In the security mode command, core network will tell what are the security capability it supported. Like these are the encryption algorithm. Like EA0, EA1, EA2, EA3 is currently this core is supported. Same like what are the integrity algorithms supported by this core network also it will share. So once the ANU send the security mode command to that UE, again UE will respond with the security mode complete message. So in this time UE will share what are the security capabilities supported by the UE side. Like previously core network shared what are the security capabilities supported. Now in this time we will share what are the security capability it will support, and at last we will negotiate and we will choose the one of the ciphering and one of the integrity algorithm. So further this message, like all other following messages, it will be encrypted and cipher encrypted messages. And at last, AMF will send the registration accept message. Like during the registration accept message, AMF will share the what are the core capabilities. Like what are the features it will support. It will support the IMS, VOPS, and the N3 data transfer, and N3 data transfer, and IP header compression, and user plane CAOT is for that IoT related supported. So like in this time during the registration accept message, AMF will share what are its core capability to that UE. Then again, UE will confirm to that AMF with the registration complete message. Along with the registration complete message, if you want to access any of the data network, it will share. It will send the PD session establishment request also. The PD session establishment request, you will share what it is APM, like access point name. So it is querying for that DN and internet, and it will share some of the policies also here. Further that AMF will send the configuration update command. In this time, Core Network want to update its network name to the UE. So, and apart from that, it will share that what is the current time zone of that Core Network also. So here you can see this is the Core Network name, like a Niral 5G. And it, apart from that, it will share the current time zone of the Core Network also. At last, AMF will accept the PT session and it will send the downlink NAS message like PT session establishment accept. In this message, it will share the what is the ID allocated for this particular UE and what is that some of the policies like the AMB, what is the aggregated maximum bit rate allowed for this UE. This UE allowed to access up to 1 GB of data for all the session, and IP allocated for this UE is 10.10.10.2. This will be allocated by the SNF and it will inform to the EPF as well. And what is the 5PA parameter? It's for the session it is 5Q9. It is usually used for the data buffering. Along with that, it will send the PV resource setup request. PV resource setup request. Like in this time, Core Network tell what in which IP that N3 interface is exposed. It will tell the tunnel ID and along with that N3 IP address of EPF as well. This is the transport layer address. So using this transport layer address, whenever any UEs want to be send any user data, like after it's receiving to the Gnode B will send that package to this IP only. So based on this, during the PD resource setup request, based on these 5QA and GBI parameters, radio will allocate that resources to that particular session. So this is the procedure until the PD session establishment accept. Is any queries in until now? Now, let's move to that GTP. This is the GTP protocol between that UE and that data plane. So here we can see this is the actual user data was encapsulated with the GTP protocol, and GTP protocol was encapsulated with the UDP, and UDP was encapsulated with the IPv4. So in the GTP, under the GTP, some of the headers, main headers like what is the QoS flow identifier, and it will have the tunnel ID also, tunnel ID of that data plane. So inside this only, it will share the actual user data. Like if you want to access any of that YouTube or like any of that user related data, this will be flow through over this GTP interface only.
So we will show, we mentioned about a management portal into the core, right? So this is the management portal, and this will give an insight of how do you configure the core, what info you see from a core. So typically, this explains basically the number of radios connected, the number of device connected, and number of sessions connected. So, one question here: can any one of you tell why the number of device connected and number of sessions connected are highlighted as separate, are highlighted separately.
Each device can have multiple sessions, correct? Means it can have a.
Yeah, correct. So basically, a subscriber can have multiple video sessions. So that is what, if one subscriber has more, that is what is be indicated there. Then this typically gives a throughput data, some alarm data, some active subscribers are connected. So this gives a topology view as to what are all the network functions present, whether a G node B is connected. Right now, since nothing is connected, nothing is C. Then there are statistics that can be seen. On the first is on the device. So on the device, user plane statistics is there. So basically, what is the uplink, downlink in terms of bytes, the number of session counts. Then at a device level, the controller statistics, like how many registrations attempts made, how much was successful, etc. Then so radio level statistics of both control site as well as the UPF site. In the UPF site, basically we can see data on all the interfaces, be it N3, N4 or N6 interfaces. The uplink and downlink bytes, everything can be shown here. Then the other aspect is configuration. So you have an APN configuration. You can create APNs, say like Internet IMX, and associate them to the subscribers. Then you can configure the network slices, the SDN and SSD numbers that you can assign. Then this is the important one on SIM. So these are the SIM details where you have the IMSI number, then you have the aggregate rate limiting on uplink, downlink, the associated slice with the subscriber. Then you also have the key association with the subscriber. Then you can enable VONR for the subscriber. So then we have an alarm manager. Basically, it tells the health of all the network function, whether it is up, down. If at all it is gone down and alarm is generated. So this is an overview of the complete management portal configuration. And so overall, these are the points that we wanted to cover today. And you have any questions?
Okay, then can we conclude for today? Is there any questions left? I'm asking again before concluding for today. Can anyone tell us
Hello.
there is any question? Okay.
Excuse me, madam.
Yeah.
How, sir, how do we integrate NB IoT onto this platform, first 5G platform?
So, the sense we have to basically have both RAN and core supporting NB-IoT, because the way it is different from a normal subscription or a normal flow is that the PDU packets all go through N2. And then there is no separate communication over the N3 from RAN onto the core side. So if both RAN and core supports this NB-IoT support on control plane, we can say basically we have to enable them, and then we have to enable subscribers to NB-IoT, so that there is no specific PDU session established. And then we'll have to handle these packets that are coming that are from the AMF, and then we will have to handle them for receiving those information.
Okay, sir. Thank you, sir.
Okay, then can we wrap up today? Okay.
Okay. Thank you, everyone.
Okay. Once again, yeah. I would like to extend my sincere gratitude to our today's speakers, Mr. Sivaramakrishnan and Mr. Venkatesh from Niral Network Pvt Limited, for sharing their invaluable insights on 5G architecture and subsystems. Thank you so much to both of you. A special thanks to all of you for your active participation and engagement throughout the session. We hope this session has provided you with the valuable knowledge and a deeper understanding of 5G technology. Last but not the least, if you have any queries, please do update in the form. Just now I sent through via chat box. Please do the needful there. And also, if you have any queries of during this course, please write to us via email. We'll definitely help you out. Thank you. Thank you so much. Great weekend. Thank you so much. Enjoy.